Now, second question that you have to ask is, how do you find the coefficients of best fit? So, in multiple linear regression, I just did the simplest case. For the simple linear regression, I differentiated something and showed the formula looks like this, and then using analogy, I showed you how the formula looks like in multiple regression, right? But you could actually sit down and derive that just by doing calculus. You can just do it by hand. Now the question is, can you do the same thing for the logistic regression? Well, it turns out that the answer is no. So there are two reasons. One is, like, you might ask, well, isn't this multiple regression? Can't we just transform the data using the logit function and then just do multiple regression, right? But then you immediately have a problem with that, because if you use the actual data on the left side, what goes wrong? The actual data is using dummy variable, right? If you have heart attack, what's the value of the dummy variable?
0 or 1.
It's 0 or 1, right? So, but if I try to plug in the actual data and then try to approximate it by this linear function, the actual data are not defined, because the data are 0 and 1. It doesn't give you a value. ln of 0 is negative infinity. If you plug in 1 here, then you get infinity in the fraction. So it simply doesn't work. So that's a no-no. Right? So that means, even though looking at it this way fools you into thinking, oh, logistic regression is nothing different than multiple regression, it's just some transformation, which by the way, I was thinking that for a while when I first looked at logistic regression. It was something really easy. But it's not that easy. And so some wrong approaches. Let me talk about some wrong approaches. Trying to do linear regression on the logit of data. This fails because the logits are not defined for the data points. So that'll be one. The second approach that seems like a good idea, but it ends up not being a good idea, is when you have so here was the data set. That was the kind of data set we had. When you just simply take this thing, the output of this is called y hat, and these are actual values y. And we were using, for the multiple linear regression, we were using mean squared error, right? What is mean squared error? First, the error is the difference between the actual minus your predicted. Squared error will be this squared. And this is computed for every prediction versus the actual. And you add them up. Okay, that's the sum of squared error. It's called SSE. But if you divide by the number of data points, this is mean squared error. Okay. For minimization purposes, it doesn't matter whether you use this 1 over n or not, so you can either say mean squared error or sum of squared error, okay? So you might think this is what we should do. First of all, even if you use this against the data and you try to find the minimal one, you can't do it by hand. There's no closed form solution that you can write down. It's algebraically impossible. Okay? So that's one of the problems. Another problem is that this, again, has the same problem of not respecting the difference between 0.99 probability versus 0.9999. Right? Because it's simply taking the face values and you're subtracting and taking the squared. Like if what you need to approximate is 0.9999, and you get something like, okay, 0.99 is your prediction, you think that these are very close, but it's not. It's very different. Okay. So probabilities at the far ends of 0 and 1 are really important, and that is not being respected if you just simply use MSE. So these are the wrong approaches. Okay. So instead, what do we do? What do we try to minimize to find the best fit? So in other words, what do you mean by this best fit? Because best fit depends on your measurement. What do you measure to say that this is the best fit? Okay, and the best to define the best fit is defined as minimizing it's called the loss function. These are called loss functions. MSE is a loss function, so it's a measurement of your prediction against the actual. Okay, how far is your prediction from the actual? The difference is called the loss function, given as summation of yi ln of yi hat plus 1 minus yi ln of 1 minus yi hat. Okay, it's this one over the entire data set. Okay, and then you put a minus. And this has a name, it's called a cross entropy. Cross entropy. Okay. Now, let's look at a few things. You see that y hat belongs inside the ln, and yi never goes inside the ln. And at first, you feel a little uneasy about this because there's no symmetry between your prediction and your actual. You're kind of treating the actual. I mean, the formula itself is not symmetric. So if you look at the formula MSE, the formula is like this. Here's your actual value, and here's your predicted value, and you just take this difference and you square it. And this is a symmetric function. You can switch the prediction and your actual and prediction can be switched, and you still get the same value. This is not symmetric. So that's like one of the properties. As a mathematician, a lot of times I look for those symmetries first, and it's not symmetric. But it makes sense because, as we said earlier, our yi's are what? It's always 1 or 0, right? So if yi itself was inside the ln, then it's going to cause a problem, right? But our yi hats, those are never exactly 1 or exactly 0. It's some value that's close to 1 or close to 0. So these don't have any problem being inside the log. Yes?
Are the yi's in a normal distribution?
Usually not. I mean, no. In many cases they are, yeah. But then the thing is, if you clap, no. Okay. The predictor variables in many cases are normally distributed, right, because your xi, the blood pressure, is normally distributed, your cholesterol is normally distributed, but the yi's are 1 or 0, so those are two distinct values. So it's not a bell curve, right. 0 or 1. So it's not normally
No,
distributed.
but the probability, is it yi, yi hat, I mean.
The yi hat. Okay, well, I think I know what you're getting at. So this thing here, it looks like the cumulative distribution function for the normal distribution. If you worked hard in statistics, if you have ever seen the cumulative distribution function for the normal bell curve, this is what it looks like, but actually it's different. There is something called the logistic distribution, which is different from the normal distribution. It also looks like a bell curve, but it's not a bell curve. Yeah. All right. Am I losing you guys today? Is too much? Too much? I mean, but you understood what the logistic regression itself was, right? It makes sense. Like you have like data points here and there, then you have a smooth surface that gives you 0 in one class and something close to 0 in one class and something close to 1 on the other class, right? And then the decision boundary will be the point where the logistic function will be giving you 0.5 probability. So that can be used as a classifier. That's the most important part, okay? I just want to elaborate further what it really does under the hood, okay? I'm trying to explain to you what's going under the hood because this is like really the basis of deep neural network. So I don't know if I'll have time to explain the deep neural network, which is the foundation for all the ChatGPT and BARD and all these things, right? Like the state-of-art things, they rely on the deep neural networks. And if you open up any book on deep neural networks, people give up because these things come up, like cross entropy comes up, the logic function comes up, the sigmoid function comes up. It's like so much math. It's just too much, and people just give up. Okay. Yes.
So what have we been going over? That's all for the decision boundary.
Right. So in other words, I'm trying to tell you that there's so much work done just to figure out the decision boundary. Okay. Support vector machines actually bypass this and say, who cares about the probability? Let's just focus on the decision boundary. And it just takes two, if they're like group A point, group B point, it just takes the line that's like perpendicular to the line that you draw here, and it's like exactly proportional. Like, it just has a different strategy of just purely thinking of these as 0 and 1. So there could be another way of approaching this, like the support vector machines, but I'm trying to dig deep into this one because if you can kind of understand this, then later on when you try to learn the deep neural network, it makes much more sense. Right? Okay, so I know your patience might be running out, but let's try to work this out further. Okay? So one thing I want to say first is that although in our case the yi values are 1 and 0s, if these values are probabilities and you're trying to compare between two probabilities, this value will be minimized when the two probability distributions are exactly the same. Okay? All right, so let me try to explain why that's true. So suppose let's just look at this function, what it does, okay? Because we have no idea what this function does. Okay? So let's just define some function f of x. Think of this as like the target, which is not changed. So it's like c, and let's say yi is c. And then you're trying to change the value of x to see what predictions should be made so that this value is minimized. Okay? So it's 1 minus c because we decided to make yi as c. ln of then 1 minus x. And then the first thing that you realize is that C is between 0 and 1. So 1 minus C is also between 0 and 1, since these are positive. But X is also between 0 and 1. If you look at the graph of the log between 0 and 1, it's negative, right? So this is negative, that's negative. Okay? So in most cases, this value will be negative. Is that fine? All right. Okay. Because you have a graph between 0 and 1 and everything is below this line, it will be something like this, and there should be some maximum, right? And we want to find when it's maximized. How do you find the maximum point? Yeah?
Take the second derivative. No, first derivative.
First derivative is set equal to 0, right? So let's differentiate this. You still remember your calculus? What's the derivative of ln of x? 1 over x. Okay. Oh, this one's harder. You have to use chain rule, right? What do you do? It's 1 over 1 minus x, and then you pull the inside out and differentiate. What do you get?
Minus 1.
Minus 1. So minus c. And then you set this equal to 0. To find the value of x that would have the maximum value. Right? Okay. Let's see, what is that? C over x plus, well, I can make this as plus c minus 1 over 1 minus x equal to 0 by multiplying the negative 1 to here. Let's multiply x and x. If I multiply x times 1 minus x to everything, you get c times 1 minus x plus c minus 1 times x equals to 0. Multiply this out, you get c minus cx, cx minus x. These cancel, and what do you get? C minus x equals to 0, so x equals to c. In other words, this function is maximized when x value is equal to c. So you can kind of see that because you put a minus there, this function, the overall summation, would be minimized if the value of the probabilities agree. Okay? That's why this makes sense. Minimizing this is same thing as trying to match the probability distribution. Okay? But then, what we are really trying to do is to minimize this under the condition that y hat is modeled as this sigmoid, as this logistic function. Okay. So each yi will be taking the x1 and x2, the ith data points x1 and x2 values, and compute it like this, and then what you're really doing is you're trying to find a beta 1, beta 2 that would minimize this value. Okay? So that's the gain. So next week when I show you the computer codes, I wouldn't be doing any of this. The computer package will do everything for us. But under the hood, what it does is it's tweaking these three parameters. These are called parameters A, beta 1, and beta 2. Those three parameters are tweaked until it gives you the minimum possible value for this. We're not really interested in the actual minimum value. We're just interested in what makes it as minimum. And if those are, the minimum is attained, then we say that is the logistic regression for the given data, which will give us the best classification with the logistic regression. Okay? All right, so far so good? It's too much? There's so much math in machine learning, which is why I like it, but I guess it's torture for some people. All right. Okay, last question is how do you minimize? How do you minimize? Well, answer is view the problem as finding minimum of some function of a beta 1, beta 2. So you recognize the function as a function of those parameters. It's a 3-variable function. Well, the most straightforward thing to say would be, oh, in that case, if you take all the partial derivatives at the minimum, all the partials should be 0, which is the way we did it for the multiple linear regression. But unfortunately, if you actually calculate the partials, not only is very, very hard to calculate, even if you did the calculation, you'll find that you can't write down the solution in a closed form. So instead, what people do is they come up with all these numerical ways to find the minimum, and they're really complicated methods just for linear regression. But I just want to talk about the most simplest one to use. The way some algorithms do this is by something called gradient descent. Who remembers gradient? So what's a gradient?
Never mind.
Okay.
I remember doing it, but not.
Yeah. Okay. Yeah. That's good. Yeah. So if it's a function of 3 variables, you just find the derivative, partial derivative with respect to a, partial derivative with respect to beta 1, partial derivative with respect to beta 2, and you make it as a vector, right? What's the geometrical meaning of this, though? That's how you calculate the gradient, but if you don't know the meaning, yeah.
Is it like the quickest way to the center?
Huh?
Is it like the quickest way to like the center?
Yeah, if the center is the maximum. Yeah. So this is called a gradient. Gradient of f is defined as that. Sometimes they write it as nabla f. This points to the quickest increasing direction. Okay. Why does it do that? Well, it has something to do with the directional derivative. So, I mean, if you want to know more, you can just search up my Calculus 3 video where I actually go through this in detail and why this happens. Okay. It has to do with the directional derivative. But if you accept this, then you see that if you want to find the minimum, you probably want to go in the direction that's exactly the opposite of the gradient. So gradient descent means move using negative gradient of f. So what it supposes is like it first starts at some random value. So let's just say a is 1, beta 1 is 2, and beta 2 is 3. I have no reason whatsoever to believe that. But let's just say that's true. That's where we begin. Okay? So that lands you in a point in this terrain. Okay? And in this terrain, you just keep moving that the direction of the negative gradient tells you. Hey, if you go this way, you can minimize the function faster. So you keep going there in that direction. And usually there's something called a learning rate, where you multiply a small number to the negative gradient and move slightly to that direction. And then you evaluate the gradient again from there to find the next direction. So, I mean, this is a 3-dimensional one, so it's harder. But if let's say you have a 2-dimensional function that looks like this. It's a surface like this, okay? Then the terrain map, this would be like a valley in a map, right? So the terrain map will be something like that. Right? So maybe a long time ago, an asteroid fell in here, and then you have like big place, and then like some abyss or something, right? And then you want to figure out the fastest way to get to this center, right? And how do you do that? Well, at each point you calculate the gradient, you move a little bit, and then you calculate the next gradient, move a little bit. Keep tweaking these values until you're at the center. And if you're close to the center, the gradient won't be varying that much. It'll be close to 0. And in fact, if the gradient is 0, then you are at the minimum. Right? So that's called gradient descent. And there's another thing called stochastic gradient descent, which is just a fancy name for saying that sometimes when you calculate the gradient, you don't have to use all of the data. You can just use part of the data. So we're talking about the heart attack data, right? Suppose we had like millions of patients' heart attack record. Then what happens is that each time when you calculate the gradient, you have to process everybody to figure out the gradient, and that's just too costly. So what you do is you just take 1,000 random patients and use that to tweak the values of A, beta 1, and beta 2. You can do that. And then in the next, when it's the next time to move, use another 1,000 that's different from the previous batch, and you keep doing that. And then if you know how sampling works, right? Even if you have 1,000 samples and you're not using the entire population, it still gives you a good idea of what's happening, right? So using samples at each stage rather than entire population, that's called stochastic gradient descent. Okay? So you use that, and under the hood, something like that is being used, and eventually you end up with the best fit for A, beta 1, beta 2, and that can be used to classify. So and that's everything. Yes?
So would you use like the best fit of all those gradients then? Like,
So you at each point you pick a value of A, beta 1, beta 2, move a little bit, which means the new value is a new value of A, beta 1, beta 2. And then at that point you have to calculate the gradient again. Using those values you can calculate the gradient again, and then you keep doing it. And because it's a partial derivative, and the function itself is like what is this? It's like it's this one, but it's inside the ln in front of yi, right, plus this other one. So it's a very complicated function. When you actually differentiate this, you'll realize that there's lots of chain rule going on. You have to differentiate the ln function, and then you have to differentiate e, and so.
Let's go.
Yeah, but that's not done in person. It's done by the computer for each of the data sets. See, those x1 and x2 are values that change for each patient. So if you have 1,000 patients, then you actually have the sum of these. So you have sum of 1,000 things, and you're differentiating a very big thing. That's why it has to be done by a computer. Yes.
So then if you're finding the gradient descent between two different points, but let's say you're doing that multiple times, is that going to give you like the mean value for the gradient descent?
No, it's just sequential. You do it once. You're here. You pick a value of A, beta 1, beta 2. Okay. Compute this huge derivative. The computer will do it for you. And it says, oh, you should increase A by 0.1, beta 1 should be decreased by 1.2, and beta 2 should be increased by 0.1 or something, according to the gradient times the learning rate. Okay, so you do that, and then now you're at a different point, right? And then with these values, you calculate that derivative again, another huge derivative, but now with different values of x1, x2, and the y's. Okay. And then you do that again, and then you keep, and then use that to move again. So you're at a new point. You keep moving until you reach the best place. You know, sometimes I use this analogy, and actually, this is true for all these machine learning with parameters. Forget all this. Okay, forget everything that I said about what to minimize. Okay, just think of like some kind of a toy, right? Where you're just given 3 dials, okay? A, beta 1, beta 2. You have 3 dials. Okay. Now, if you control this wisely, what it ends up doing is it will change the decision boundaries, right? Okay. And then there's one decision boundary which is like the best, okay? So what do? You just keep tweaking, right? And the stochastic gradient descent that I just explained is just one strategy. There are several other strategies of getting this, okay? So you take the dial, move it, tweak a little bit, and it says, oh, it's now better, right? You take the A, beta 1, beta 2, just tweak it a little bit, it gets better or worse. Okay? If it's worse, then you're doing it wrong. And what you do is, the stochastic gradient says that if the system reacts smoothly with your change of the dial, what happens is that if you tweak slightly, you can look at the rate of change, right? And the basic strategy is this. If you rotate a dial while the other is fixed, this is another way of saying partial derivative. If you rotate the dial slightly, and if the rate of change is big, that's the one that you really have to change a lot. Okay? If the rate of change is small, you don't change that a lot. Okay? And then you just fix the other ones, rotate slightly, measure the rate of change. Now fix the middle one, rotate slightly, figure the rate of change. Fix the other 2, rotate slightly, figure out the rate of change. And then once you have that, now you have you go back, make the dials go back to its original position. And now, using the learning rate, you move in the direction where the system becomes better. And you rotate the dial proportion to the rate of change. Something that changes a lot should be changed a lot. Something that doesn't change a lot, that means you're probably at the best place. That's why it doesn't change a lot. Have you ever used those old radios where you have to change the station using a dial? And a lot of times you see that if it's near the correct position, the signal doesn't change a lot, right? But then if you are away from the best position, then it goes bad pretty quickly, right? So that's the idea. The ones that don't change a lot, you're pretty close to the good place, so you don't change a lot. Okay, so it's just a game of trying to figure out the best fit, and at the end of the day, what you get is the best parameter. And if you have the best parameter, that's it. Yeah. So if you think of it that way, it sounds a lot easier because there's no math involved, right? Okay. Another question? Yes?
So when we're adjusting the decision boundary, are we just adjusting like this way, or are we like...
It's moving all, it could be like this, it could be like this, tilting.
But is it always just going to be straight?
Yeah, and by the way, I'm just using a two-dimensional one, two predictor variables. If you have like 3 predictor variables, that's like a plane that's being moved. And in practice, in many practice cases, you will see that the predictor variables are like 10, 11. Then it's like in a dimension that you can't even imagine. So it does become pretty powerful if you have lots of predictors. Okay, that's all.